Afternoon, everybody. I think we'll get started. Thanks for joining again today for the next talk in this series. We're going to be doing something a little bit different from the last couple of topics that were more network focused. DK from Ohio State was more than happy to give us some of his time today to talk a little bit about what's going on with AI and the NSF-AI Institute. So he's going to go over a little bit about ICICLE. And he said that there's a couple of videos in here as well. And if you do have questions, just type them in during the chat and we'll make sure that they get answered. So I'll turn it over to DK.
Okay. So thanks a lot, Jason. Thanks for inviting me to share some of the things what we are doing. As many of you must be knowing, NSF has invested heavily on AI. In the last 3.5 years, there are 25 of such institutes have been formed. And each institute is like a $20 million. It's a very multidisciplinary kind of activities. And every institute also has one special objectives. And so we were funded in November 2021. So we are around just finished mid of the 5-year plan. So the institute is called ICICLE, and the bigger focus is to really design intelligent cyber infrastructure while trying to democratize AI. And that will be the focus of this talk. And as Jason indicated, I mean, if you have any questions, please feel free to post it in the chat. I'm monitoring the chat, but if I miss something, Jason, please interrupt me. Okay, we can have it as a dialogue as we go on. So if you take a very broad look at the field of computing, here I go back to 1975, almost 50 years back. This is where like the traditional scientific computing started, gradually morphed into high performance computing. Then in 20 years, around 2000, the big data analytics came. So we had not only computing, but we also had the data. And then people came up with newer paradigms to make sense out of a lot of data. And of course, in another 10 years, we went into the field of AI, and that is booming over the last 15 years. But there is something else is also happening at the same time, and that's what is the focus of the ICICLE. And since many of you are involved in the ESNet, I think it is very familiar to you, like a computing continuum. So the left-hand side shows the traditional HPC AI, big data. When you operate on those, the data is typically centralized, might be, or you move it to a parallel file system, and then you perform the operation, and then the results are available. But currently, this field is changing. This is the computing continuum where data is no longer static. It's very dynamic. Data is coming from sensors, from drones, medical instruments. Every field is trying to expand into these kind of newer kinds of platforms. And there the question is where data is being generated, how the computation is happening, who is doing the computation, how the data is moving. So those are the open challenges. And that's what is being captured here. So if you take a computing continuum from starting from like a sensors to near edge, cloud, and HPC systems, the data can move here between the traditional internet or even the ESNet. And this is what is a big focus in the ICICLE Institute, and I'll gradually include those things. So the broad idea is that this computing continuum actually will, in fact, is gaining momentum, and you will see that even more and more when billions of people have internet of like the iPhones and all these things, data, computations, they're all getting merged. So how do we create this kind of intelligent cyber infrastructure for the modern AI era in the computing continuum? And not only we come up with solutions, but make these lower barriers so that people can start using this. So that is also another focus here, to democratize the AI. So before I go here, I'd like to thank, I am presenting on behalf of the ICICLE team members. It's a very large organization. This is a photo of, we had the all hands meeting last year. We'll be having another one this year. So the talk will be divided into these major 4 parts. I'll start with the ICICLE vision and its goals, try to give an overview of the research challenges being addressed, and I'll just select some highlights. It will be very hard to cover all the accomplishments in 1 hour, but I'll conclude the talk with saying how do you how to get engaged. If some of you are interested in collaborating with us, we'll be very happy to talk to you. So let me start with one such example, just to give a perspective. Agriculture. As you know, the agriculture is becoming very important as the world population is increasing. There is always this big issue of food. How do you harvest, or how do you raise the food with the lowest cost, and not only just the cost, but also having good kind of like a impact to the economy, or to the society. In the traditionally, let's say there's a farmer had a large field, he or she has knowledge. Let's say some diseases have happened. He or she can actually go around and see, oh, this is the disease, then go and then spray this kind of pesticide. Now, of course, this is a very time-consuming task. There is a lot of automation is happening over the years. Tractors and all have been used in the past to even to seeding, to harvesting, and all those things. Now the question is, can we make this AI driven? Okay, so this is in fact in one of our focus use inspired science cases in the institute. So just imagine like if you have drone, I can actually put and there is let's say there is a crop, and crop can have different kinds of diseases. If I can build different AI models for that crop and the diseases, I can actually carry that model in a drone, and the drone can actually in real time go and take pictures and does the inferencing and can decide what kind of disease have happened. Of course, there are different drones. We'll see some drones may not have enough memory or compute power to do all the tasks. They can just take images. Then in that case, we can send those images to cloud or to the HPC centers to perform the inferencing and give the results back. So if we can automate, in fact, we can even go one step further, not only like the drone decides or like comes to a conclusion saying what kind of disease have happened, it feeds that information to the tractor on the ground. Okay, so the tractor automatically can go with appropriate cameras and all those things, can actually go and spray the appropriate pesticides. Okay, so think of if we can achieve this, this will be like a precision digital agriculture. Okay, so automatically we identify exactly which part of the field has what disease, how much to spray, all those kinds of things we can do. This is just one example, but there are hundreds of examples in the agriculture field itself, and I'll go into more details later on. So if we map that into this bigger field of the digital agriculture into the computing continuum, we need to actually to come up with a final solution. We need to, of course, solve a lot of challenges. So for example, how do we develop the cyber infrastructure for autonomous self-driving farms? How do we do rapid data generation? How do we come up with like a different kinds of architectures, like here the AI model architectures, data sets? How do we collect data from different farmers, different countries, different states to build those models, because those models have to be very accurate. And especially here, since we are talking about like the drones and all flying, they need to talk to edge devices, and it depends on like at any given time, as we know, like a wireless may not be very strong, or depending on the location, how the drone is flying. So a lot of these solutions need to be then made adaptive. Okay, so that's why we have this focus on called adaptive AI. And of course, in the end, we also need to have privacy aware data sharing, because we'll be collecting a lot of data. And in the end, in all these things, we want to do pass to the farmers in a very low overhead. That is our democratizing AI. So we want to, there's a big focus here on the conversational AI. Okay. I mean, we can't ask the farmers to learn PyTorch or distributed PyTorch or TensorFlow and then run the programs. We want to convert everything and convert that into an app, like a iPhone app, and they might be able to subscribe this like a $9.99 per month, just like Netflix or some other organization. So then they can talk. The farmer can talk to the to the app in the morning, say, okay, what kind of diseases have happened in my field? What should I be doing? If it is a harvest time, should I be harvesting it today or tomorrow? Because a lot of things can happen. Not only you harvest it, but you have to send it. What is the market price? If I delay it by 24 hours, is the weather will get affected, like my harvesting will get affected by weather or not? So a lot of these kind of questions come, and we want to make these farmers jobs very simple. Okay, but at the same time, we want to make this kind of cyber infrastructure so that it will be much more beneficial to the farmer, and the farmer can actually make more profit. And at the same time, we want to make sure that the crop is being produced with lower cost and also with a good impact in our environment. So all these kind of solutions we want to solve. So this is one of our example use case in our institute. The other one is animal ecology. So here again is this very similar. Animal ecology, as many of you might be knowing, is the understanding the functioning and behavior of animals in the groups in the context of environment and evolution. So even though over millions of years we have existing with animals, we have not still understood all their behavior, all their patterns. So here the question is, can AI be used? And similar kind of challenges exist here. If you think of, like, I'll introduce kind of a concepts of camera trap or drone. So let's say in Kenya, there are different herds of elephants are moving. How do we understand their behavior? Can we actually fly drones and get pictures, get videos? And based on that, can we build the models of how they are actually performing? Okay, or how they interact with each other as well as with humans. So there are a lot of these kind of devices come where not only drones, camera traps, a lot of devices are being designed. So there is a lot of, from the computer science perspective, there's a lot of trade-offs here, resource versus delay. If the device, like a camera trap I'll introduce later on, if it has only like a limited kind of power or a memory storage, it can operate might be for 2 weeks. So then let's say new animal it detects or a new kind of a incidents occurs, how does it actually communicate to the cloud, or how does it communicate to the database? So like this, we need to totally understand this data movement and computation in the computing continuum to have a good solution. The third example, which is another societal challenge we address in our institute, is the food distributions. I talked about the agriculture. This is more like a harvesting. The crop is being raised, but how do we distribute it? And that is a big challenge all of us face. Like when I say all, like the society faces. Many of you must have heard of, like, in or seen during the pandemic, a lot of farmers in Florida were dumping their crops because there was no way they were able to move these things. On the other hand, in Ohio, a lot of people were standing in front of food banks. Okay, so how do we bridge this kind of a gap to make sure that we address the food supply chain vulnerability, address high food insecurity, minimize food waste, have negative environmental footprint, so that we have a holistic food systems planning. So here again, you will see when mapping into the computing continuum, we will see a lot of these, like there are diverse data sources of database. We need to come up with database federation, heterogeneous and food systems and actors. Here again, we need like a conversational agents. We need a existence of large knowledge graph. And also many times, since here, let's say a store manager or a truck driver, they are operating on some components, even text becomes very hard for them. So how do we develop like intelligent visual analytics so they can understand and take decisions? So these are the kind of the three use inspired science cases we have. And but by now you would have seen, like, if we can solve these at least three problems, many more situations we can address. All of them have very similar situations, like smart cities, smart manufacturing, smart transportation, real-time surveillance, the entire field of medicine. Everywhere this computing continuum is coming, and we want to design the next generation intelligent cyber infrastructure for those systems. So that leads to, this is the actual broad challenge of our institute, to design the next generation intelligent cyber infrastructure for this computing continuum with heterogeneous resources, because computing continuum is evolving. Every month you see newer kinds of sensors, drones, devices, edge devices, even accelerators, GPUs. All these components are evolving. So how do you come up with a design which can actually be adaptive, which can be plug and play? That's what also is a big focus in our group, so that we can actually solve these societal challenges. So with this, let me introduce a small video here. I think you should be able to hear. Let me play it. If you don't hear, give me a ring. Just a minute.
A policymaker wants to know how land use policies will affect a region's biodiversity. A farmer is concerned about how new weather patterns will affect crop yield, while food distributors and public health officials are concerned with how supply chain disruptions will affect deliveries of nutritious foods to communities. Current technology can provide data and models to tackle grand challenges such as biodiversity, conservation, and agricultural and food system resilience. But it still lacks the infrastructure to link across data and models seamlessly to answer complex questions from diverse stakeholders' perspectives. Even AI experts are challenged to create standardized solutions across domains because a standardized cyber-infrastructure integration with AI just doesn't exist. Enter ICICLE, Intelligent Cyber Infrastructure with Computational Learning in the Environment. ICICLE is an institute dedicated to building a national AI-driven computational infrastructure that functions as a utility, much like our electricity, water, and transportation infrastructure. This new utility will enable the delivery of AI to end users with the flick of a switch, enlightening solutions for imminent problems of national, regional, and local importance. ICICLE will provide an operational rationale and framework for a cyber infrastructure that delivers wide and easy access to smart computing, plus a conversational interface that allows stakeholders from diverse domains to ask questions and receive answers informed by currently available data and knowledge. For example, food distributors, emergency food agency managers, and logistics company executives might ask, which food supply chains will likely be affected by an approaching storm? The ICICLE conversation agent might respond with, I will predict future states of your regional supply chain under forecasted weather scenarios and evaluate alternative scenarios. Okay? Upon confirmation, ICICLE would then retrieve satellite data on weather, connect to weather forecast models, acquire inventory data for food producers, processors, distributors, transportation networks, wholesalers, and retailers throughout the region. Use AI models to forecast supply chain conditions from a baseline and alternative logistics that maintain consistent food supply for vulnerable populations, and estimate supply chain disruptions based on historical and current data from other locations, mindful of privacy. ICICLE will go even further by accessing high-performance computing centers to backcast and learn how reconfigured landscape-scale precision agricultural production and distribution systems could integrate with alternative supply chain infrastructure to avoid similar future disruptions. Using an orchestra of smart cyber infrastructure elements, ICICLE produces a symphonic answer that improves outcomes for diverse stakeholders. ICICLE holds the potential to transform today's AI landscape from a series of fragmented tools for use by a few to one where democratized AI and integrated plug-and-play architecture empower diverse end users with knowledge and data flows that are science-based, traceable, transparent, reusable, and trustworthy. Introducing AI for CI for AI. AI for everyone.
I hope that gives a very broad perspective of this institute. So in a nutshell, here you can see, like, I talked about this computing continuum. These are our three use-inspired science cases, and this is where the ICICLE, the main cyber infrastructure components fit in. Of course, inside this there are multiple components. I'll be gradually introducing those. So these are very large organizations. Ohio State University is the lead. I am the overall PI. But we have another like 15 universities, organizations involved. There are like 33 faculty, 41 staff, around like 70 students. So it's a very large institute, almost like 150 people working, and we have a lot of these collaborators, including some of the other also NSF-AI institutes. We have also gone global. We started this in US. Last year, we got a funding to expand our work with the Indian Institute of Technology, Bombay, because the agriculture field or the agricultural issues are worldwide. Okay, but the solution need not be the same. For example, let's say in Ohio, we focus on soybean. Might be in India, they're focusing on potatoes or onions. So the similar ideas will work, but they have to be contextualized, and then appropriate changes need to be done. And gradually, actually, we are in discussion with several other countries, and we'll see how that goes. So as I said, we started this project in November 2021. It's a 5 years project, so we almost finished like a half of the time frame. So let's see what are the research challenges being addressed. So if you see this example, we saw that in the video, like a SOP manager asking the question through the conversational agent to see, okay, there is an approaching storm, where should I be moving, or what of my supply chains will get affected. So to provide answers, so these are the different thrusts we have. Like we have the foundational systems AI, then the CI for AI, that is the cyber infrastructure for AI. This is something new. I'll also be talking AI for CI, not CI for AI, but AI for CI. We have software architecture. We have this visual analytics for explainability. We saw that in the video also. And then, of course, there's a big focus on privacy, accountability, and data integrity. And of course, we co-design these with our science domain. So in our team, we actually have many non-CS faculty. So these faculty members are from agriculture, from distribution, nutrition, those kind of different areas. So we are actually working with them to see what are their requirements, where the obstacles are, and how do we design our cyber infrastructure so they can work together. So let me just quickly go over some of these details. Again, we may not have time to go over all details. So this is like our foundational systems AI thrust. So these components basically address AI complexity and heterogeneity for that plug and play aspect I talked earlier. So within that, we have several sub-thrusts. So one of the bigger focus is the knowledge graphs, because as a lot of these data sets are coming, how do you actually present the interaction? So this is where we have to have multimodal knowledge graph to encode and region, reach data modality, construct those things, and also interplay with the LLMs. Similarly, we have model commons. I motivated saying, okay, these drones are there, but in the end, there could be hundreds of drones with the different characteristics. So how do you select which model to be used and for what scenario? It will depend on the battery life of that drone or the memory or the computing power. So you want to design here is like a model commons where all the models will be there. And based on the need, automatically it will be able to detect or find out or select what model to run. Similarly, we have adaptive AI, because I gave an example of that wireless. If there is not enough bandwidth, we need to change the strategies. There is a big focus on federated learning, because to build all these models, we have to get the data from a lot of farmers, cooperatives, but many of them may not feel comfortable in sharing the data. So this is where the federated learning comes. And of course, we are in the exciting phase of all this conversational AI. We want to make these much more grounding LLMs, reduce the hallucinations, and also provide complex reasoning. So then the next one is CI for AI. This is our traditional thing. Many of you might feel related to this. These provide the necessary cyber infrastructure to deploy AI throughout the computing continuum. So we have high performance training. How do we take advantage of the latest CPUs, GPUs, AI hardware? How do we do the data management? How do we move data seamlessly between, let's say, cloud to the HPC centers, to the edge devices? A lot of focus on the edge intelligence, depending on the characteristics. We have people in the wireless team also. Like they are trying to come up with, for example, depending on a situation, if a lot of frames are being dropped, automatically the system can actually use different kinds of compression, different kinds of encoding, so that the time doesn't get wasted. And of course, you need to do the control and coordination. So this is something new. AI for CI, might be some of you might be working in this area. So here the idea is that how do we enhance CI for AI for adaptive and field optimized machine learning? So let me motivate it through one example. Many of you, I'm sure, familiar with scheduling, job scheduling. Job scheduling has been there, I mean, since almost 30 years. People have a lot of algorithms, many HPC systems, even the networks, they follow a lot of the scheduling, but those are all algorithms driven. Okay. I mean, literatures are there. There are a lot of solutions. They follow some algorithms. But sometimes these algorithms are very complex, and more complex algorithms have not been utilized because of the overhead associated with it. Okay. But now, can we change that into an AI approach? Okay. So if we have a lot of data, let's say we have millions of jobs have been submitted, or millions of flows have happened in the network like ESNet, can we log those data and then build AI model using that data? Okay. So then the next time, if we can build that model with a very good accuracy, like a very high 98, 99% accuracy, so the next time a new job comes or a new flow comes, we can actually use that AI model just for an inferencing, which will be much more faster than running this complicated algorithm-based solution. So that's what we are exploring here in all different aspects. Here I gave an example of scheduling. I'll show some solution later on, but you can apply it for optimization level, the middleware level, applications level, etc. So then I talked about this privacy, accountability, and data integrity. This is where we want to provide transparent and trustworthy solutions. Up to a certain extent, AI ethics also come, but our institute is not fully based, like working on all ethics. There are separate institute, they are focusing on these, and we want to use the best practices from their institute in our solutions. So here, for example, here it says, for example, in our digital agriculture case, where stakeholders, it could be farmers or industry partners, are comfortable contributing data and AI models for ICICLE AI research, and might be broadly for the AI research. So that's what this focuses on. So then we have these visual analytics. I indicated, since we are providing conversational AI, of course, we can give the decision, but many people would like to understand what is going on behind the scenes. So this is where we have a dedicated visualization team working between data, models, knowledge, and user interaction, and present the solution in a much more visual manner. So I'll show some examples later on. And of course, I talked about this co-designing, which we are doing with the UG and Smart Science domains. And of course, this ICICLE Institute was funded from National Science Foundation Office of Advanced Cyberinfrastructure, or OAC. If those of you know about the OAC, they actually want the software to be delivered. So we have a big focus on putting together the software stack. And here we are actually leveraging the software framework called TAPIS, TAPIS, which has been developing at the University of Texas, Austin, at TAC. So we are actually building on top of that, and these different kinds of color coded indicate how we are bringing those newer kinds of solutions to build the entire software stack. And we have actually made a lot of releases. I'll talk about that very soon. And then of course, the bigger thing is also the broader impacts. This is very important because it's an NSF-AI Institute addressing DEI, BPC, workforce development, and the collaboration and knowledge transfer. So with this background, are there any quick questions here from anybody?
No questions yet.
Okay. Thank you. So let me continue. So this section, I'll try to show some of the selected accomplishments, and that to also highlight. I'll go into like some of the software releases we are doing, and I'll talk a little bit about 3 of these, like the digital agriculture, animal ecology, smart Foodsheds. I'll have an example of that intelligent scheduling I talked about, like AI for CI. So these are the components. Like every 3 months, we are making releases. So here you will see, like we started from like last April. Every three months, we are releasing. And some of these are components at this time. They are not end to end, but we are allowing the community to grow with us. People can actually, in all these different areas, they can actually download. These are all available here. You can go and register and then download. And we'd like the user base to increase. So in fact, next month, there is a PERC conference. If we are actually launching a user group, ICICLE user group, we call it IOG. So we'll be formally introducing that to bring all the stakeholders and the users together. So then these are some of the other releases we have done in the recent months, and then there's a new release coming out next month.
DK?
So now, yeah, go ahead. Yeah.
One question did come in. Does
Mhm.
ICICLE have its own computing infrastructure,
Yes.
or are you using other people's?
At this time, if I didn't go into within our institute, we have actually partners from TAC, SDSC, and we have supercomputer centers. So we have 3 supercomputer centers involved. So at this time, we are mostly leveraging their resources, and of course the cloud. Okay.
Okay,
So
thank
that
you.
is the kind of the environment we are leveraging. We are also a part of the new NIAR, the National AI Resource Infrastructure. If you remember, we are participating there. So through that also, we'll be able to actually work with the other people in this AI community. So let's move to the digital agriculture. So I'll go into a little bit details here. So this is like a very quick overview of the digital agriculture team. But if you really go down, I mean, you remember like in the very beginning, I introduced the concepts of bringing AI to the digital agriculture, but it's a very massive challenge. Okay, so here if you see like this is like what is input, output, partner engagement. So just to see from crop health diagnosis, there are a lot of aspects. I just talked about disease, but it could be residue cover on soil surface. What is the soil aggregate, crop development, non-uniform emergence, nitrogen deficiency, defoliation, crop blight. There are a lot of issues these farmers deal on a day-to-day manner. So how do we really take the data and then provide our solutions? And in the end, like this kind of things, what I said, like the drone creates a heat map saying that, okay, is the field is good or not, or even put the things into the tractors. So this will be the corrective action, like a selective spraying, nitrogen use efficiency, yield estimation, replant decisions, tillage control. So all those will be the kind of the real actions we need to make sure. So in that context, this is a very complex slide, but that's what we have been working on. Actually, the digital agriculture, you can think of it as the entire architecture where we go through data repositories, model repositories, go through these all different kinds of components here. I'll show it through a demo. It will be much more easier to understand to have a complete solution. So this is the kind of a workflow we have actually developed, and it is running in some of the supercomputer centers. So the broad thing is the data collection and pre-processing. So how do you collect by drone to edge, data geotagging, plot the extraction, then we have to do the model training, data selection, class definition, hyperparameter selection, model selection, data labeling. So like this, and then inferencing their visualizations. There's all these steps involved, and we need to develop this entire workflow so that a common farmer or any company can actually use this and provide solutions based on this workflow. So let me go into a little bit more details. I'll first start with data collection, labeling, distributed training with semi-supervised learning. Then we'll talk about some quantization in edge devices, aerial crop scouting, and how we are putting this end-to-end CI. So this goes into a little bit more details. I talked in the few slides earlier. I mean, these are all these issues. Like, let's say we are doing a non-uniform emergence. Our eyes are very powerful. We can see it, but how we can develop computer vision-based AI solutions or models, which can say that, oh, this emergence has not happened properly, or how, like this field have like a European corn borer or corn leaf aphid. And we have actually solutions for some of these, for not all. Actually, a drone can fly very low and actually catch these things. Okay, in an automatic manner. I'll give that solution a little bit later. So then the question is data labeling. Okay, so you have a lot of this. For example, to detect a disease in a crop in a very accurate manner, you have multiple solutions. Either you have millions of these images, okay, and somebody has to do data labeling. That is very expensive. But then the question is, if I don't have all the data levels, I cannot do totally supervised learning. So I need to go into some semi-supervised learning, and that's what we are focusing on. And we have solutions where even if we use only 1% of the data with a good levels, we actually provide accuracy up to 97% kind of thing. And that is the approach we are taking here. So we have designed we call it harvest. high performance artificial vision framework for export labeling using semi-supervised training. So it has all the steps. So we are trying to actually make it available as a service. So we call it like a digital agriculture service. So it could be running on an HPC system, or it could be running on the cloud. You can actually, any end user can actually, through a portal, interact with this service. And you can actually, the user can bring his own data or the model, or both. Okay, so that's what we are allowing, like a bring your own model, BIOM, bring your own data, BIOD, and then the system will actually interact. You can interact with the system, and then you have the final model available to you. And this has all the, like if you think of like starting from the deep learning, all the harvest different kinds of training engines, use below all the different DL frameworks, and distributed middleware. We use all the different kinds of libraries, MPI, NCL, CUDA, CUDNN, kind of things which will run on different CPUs, GPUs. So I talked about this case. We'll see it in a demo in the next slide. But we have actually done this kind of like a plant stress identification on 2 different corn crops and soybean crops. Originally, we were giving this like you see almost like a 10,000 samples, 5,000 samples. But using only 80 labeled samples for class, we are able to give 97% and 93% accuracy. This is like the semi-supervised learning. We presented this paper at IEEE Big Data last year. And then you can get also very good performance. We have parallelized it, so it can run on a cloud cluster, on the cloud, or a cluster. And let's see how it actually works. So here again is a small video I'll play.
This is the SSL pipeline for digital agriculture classification use cases. It addresses the bottleneck of expert labeling by using state-of-the-art semi-supervised learning techniques. The software is currently running on top of an HPC system, and we're accessing it using the Open On-Demand portal. The first step is to define our use case. We just need to enter a pointer to our dataset and a list of classes to be used for labeling. For this example, we're going to use the weed detection dataset. Now we hit submit, and an unsupervised learning job will be scheduled on the HPC system to cluster the data. Once the data is clustered, it's presented to us, and we only need to label a few samples for each class. The total images we need to label here represent less than 1% of the overall dataset. So we labeled 2 classes so far. Now we need to label the soybean class, and finally the broadleaf class. After we finish the labeling, an SSL job is scheduled on the HPC system, which trains an accurate deep learning model using both the unlabeled data in the dataset and the small sample of data that we just labeled. Once the SSL job finishes, we can either download the trained deep learning model and use it directly for inference, or download the fully labeled dataset.
So this is where actually, as you can see, this is like a service, and we are actually allowing the end users to interact with this service. Okay, so we are not just blindly taking all the data, just like you saw the selection. So here we expect the farmer or somebody is very familiar with that kind of a crop or disease to actually select, saying, okay, these are very high quality images, and based on that, we can actually build very accurate. Okay, so that is the kind of a training. But now let's say we want to fly these kind of drones. As I said, like there are all different drones. This is where inferencing will taking place. So we are currently studying in a very exhaustive manner all different kinds of drones, their capabilities, even starting from like Raspberry Pi to Jetson, all the devices we are seeing, and what kind of like inferencing engines we can run, and what will be their characteristics in terms of power and memory requirement. Okay, and of course we use the quantization things also. We presented this paper at Fog and Edge Computing Conference last year. So then this is the other component, which is the actual flying the drones and all. Okay, so this is my colleague, Professor Chris Ward from the Computer Science Department. He's working there. So he has actually capability. You can actually run 15 feet above the ground. the drones, and these are being run. We have a collaborator in Ohio, La Rui Farms, and you can actually run multiple of these drones. If you have a very big field, you can actually fly all these drones, and they can actually work in parallel. Okay, so we are actually taking parallel computing to the edges. Okay, and they will work together, do this kind of inferencing, whatever we talked earlier, and come up in the end, it comes actually with a heat map like this. And this is two color, saying whether disease is there or not, but it can be also multicolored. That is the kind of a next step we are thinking. So these packages are actually available here, software pilot, OpenPass. So these components are available. So in fact, if you have a drone, you own a drone, you can just download and see how actually it works. So like this, we are enabling the community to really get engaged with us, and then work on this. So our broad goal here is to really take things from the crop health issues and really going into the HPC enabled data harvesting, preparation, HPC for ag, for AI, HPC to the field, and then finally link it with the crop management intervention. So as of now, like we have some of these components working, some of them are integrated, and we expect by the end of this project, we will have the complete solutions ready and be available for users to use it. Any questions on this digital ag piece? Is the idea clear?
Yep, no questions yet.
Okay, good. So let's go to the animal ecology. So similar kind of things exist, but it's a little bit different. So I don't know how many of you are familiar with camera traps. Okay, so the camera traps is actually a small device you can actually mount in different places in the campus or even in the wild. So the broad thing is that it detects different kinds of species, okay, in the wildlife habitats. And many times you have little or no network bandwidth. You have to conserve the power. There are a lot of CPU and memory constraints. So in that context, there are a lot of techniques are being used, like how best we come with a better vision model, adaptive AI, OOD detection, continuous learning, neural architecture search. So what we have done, we have actually built a simulator dashboard, because many users don't know, like saying, okay, I have this kind of a camera trap from vendor X. What can I use it for? Okay, what will be the capability? So we are first trying to do characterization and then converting that into a simulator dashboard, so that the end users can actually interact, plug in this different kind of, let's say, should I use mega detector V5 or not, mega detector V11 or not? So like this, they can play around, and in the end, they come up with their own kind of a solutions, which they can actually deploy in the camera trap. So then in the smart food distribution, here, like I introduced these challenges, like there is a food system lacks resilience, there are many different actors, access to data is difficult, need a common framework. So here we are trying to develop in a step-by-step manner to bring all these diverse actors together and their databases, their repositories. So we have developed like two phases. The first phase is, we call it a P-pod. It is a schema that describes the attributes and relations between persons, projects, organizations, and data sets. And the way we are trying to design it next, you will see a little bit of a small video again. Currently, it has been instantiated with real data from California and Ohio. But it is generic. You can take this model and let's put the Illinois data there, or any other state, or even any other country. You can feed the data and you will be able to interact with it. So these are like quickly our the team. Let's listen to this demo.
Use case 1, Partner Finder in the Smart Foodshed. Our user, Alice, wants to find possible partners in the food system. She first drags a data loader to load peapod link ML file and vocabulary file. Then she connects it with an ontology filter to create the ontology of peapod. Later, in order to find target partners, she first adds the filters of use case and position type.
So this is the knowledge graph I was telling
Then she
earlier.
lassos the entities of interest. Our ontology filter will automatically generate the query based on these operations. She later drags a query editor to check the generated Sparkle query. Also, she connects a KG querier to fetch data from the peapod knowledge graph. The output can be displayed through a table viewer. From there, Alice finds possible partners to collaborate with. Our second use case is how to visualize data automatically. First, Alice selects a data loader to upload a local CSV file. She connects it with a table viewer to display and filter the tabular data. Then, she adds a table visualizer in the pipeline. It will generate a set of candidates and randomly render 4 charts to display data patterns. We further allow users to download pictures and check the specifications of the chart.
So this
Use
kind of
case
like
one.
sorry. So this was like the first phase. We had only graphical things, but now we have brought our LLMs, conversational AI. So this is like we call it like a Viz Studios. So one can actually question. You saw that in the video. Like for example, like summarize the project related to the issue of water pollution. So you can actually ask these kinds of questions based on the knowledge graphs we developed earlier, and then it will actually give you the answer. So you have done all these interface design, architecture, the backend, query processing. So there is a small video here again. Let me play. You will see that.
Suppose we want to explore potential collaborators working on water quality issues in the food domain. We type in the query and click the search button. In the backend, multiple processing steps occur. First, entities are extracted from the user's question. Then, those extracted entities are mapped to possible classes, defined by the knowledge graph ontology. Sometimes, the exact matched entities cannot be identified from the user's query. To resolve such uncertainties, the top 5 entities with the highest semantic similarity are displayed, measured by embeddings generated by language models. The color indicates whether the entity class matches the previous mapping results or not. Additionally, the top 200 semantically similar entities are shown for users to explore. By hovering over each node, they can find more related entities existing in the knowledge graph.
So here again, we are trying to make it so simple so that the end user doesn't have to spend like hours and hours to get different data, operate on it, process on it. So through these interfaces, they can actually get answers to their queries in a very fast manner. So then the thing is the intelligent scaling scheduling. I talked here. Let me go into. We're running a little bit of time. So this kind of a project we have been running is called HPC Application Runtime Predictor. Okay, you remember I talked about like a scheduling. Instead of doing algorithm based, can we actually do AI based? So there is a lot of different models here based on like how it runs on different systems. We have actually taken all those data and built an AI model. So we call it like a HARP, HPC Application Runtime Predictor. And this paper was actually presented at PERC conference last year. But based on that, we are now able to actually think of like the drone flying. If we know exactly what model is running, what kind of computation, it will automatically say, oh, at this time, let's say on the TAC, so much capacity is available versus Azure, so much capacity is available. Based on the cost, it can actually direct that job to the appropriate HPC or cloud. So that's where we have like a kind of a smart scheduler framework. This also has some intelligence plane. It can actually interact with a lot of different data repository, model repository. And as a part of that also, like sometimes we have done like this control plane. We call it like a performance function as a service. So we are developing this small component. One of them is called this elevator, and that actually supports GPU and delivers very good performance compared to like there's a competitor which is there, OpenWhisk. We are able to do it almost 100 times faster. And then in this entire workflow, as you know, like there is a lot of importance into the compiler, the code optimizations. So this is where exactly we're taking the workflows and seeing where the bottlenecks are and determining what optimizations to apply and where, so that the end-to-end workflow can actually run in real time kind of things. So these are some of the, again, the highlights. There are a lot of other things we're doing. Unfortunately, we don't have time to discuss, but let me conclude this saying how to get engaged. So as we are working on, as I said, NSF has given funding to these 25 institutes. So many of them have different objectives. So our focus is on the cyber infrastructure. So here we have actually signed MOU with some of the other AI institutes because they have exactly similar needs at the cyber infrastructure level. They are focusing differently. For example, let's say Ag-Ed, this is based on Washington. They're focusing on robotics, but in the farm. Like how does the robot actually goes and plug orange or even strawberry or blackberry kind of things? But behind the scene, they need all those training, inferencing and all. So we are working with them. Similarly, all these other institutes. I mentioned about this TH Mumbai in India along the digital agriculture. We are also working with some of the companies. They are interested in taking our solutions. The one of the biggest company, this is based on Brazil, called CNH Industrial. So they actually dominate all the intelligent tractors. So we are working with them to see how our solutions can be deployed there. Similarly, TCS India is also heavily into digital agriculture, and we are talking with them. So we can have multiple levels of collaboration and engagement. Of course, the first thing is to, as I said, like we are releasing all the software. If you're interested in playing with it, installing on your version, we'll be very happy to work with you. So please go and register yourself here and download the things. In general, also, we can have like a different levels of students, visiting research fellow, academic collaborator, industry partners, and we have like a 2 mailing list, ICICLE Announce and ICICLE Discuss. You can register them to get updated. So to conclude, the broad agenda here and the ICICLE Institute to really design the next generation CI through co-designing with the use-inspired science domains. And our current work focuses on these 3 science cases, but as a motivated, once we have solutions coming, we can actually get engaged with all these different domains like health and medicine, environment, communication, collaboration, manufacturing, AI for social good. In fact, we are having some discussion with Honda. If you remember, if you see like Honda, all this manufacturing, car manufacturing takes place, robots are doing the welding. How do you quickly know that the welding is proper or not? Okay, if you detect that in the quality assurance at a very late stage in your pipeline, you are losing the performance because you need to take that out. So this is where we're actually working with some of the related companies to bring AI models to welding and exactly use our training, inferencing framework workflow, which I talked earlier, to get embedded into their system. And similar examples, many other situations exist, and we are talking with some of them. So with this, let me conclude here. So the ICICLE is basically the broad objective is to have a global leadership in computing plus AI, the integrate into the national CI ecosystem, leverage the existing capabilities, be collaborative, and be sustainable and inclusive. So please join with us. I'd like to thank all these people. These are the actual heroes. I'm just talking on behalf of them. These are all the faculty, student staffs who are working here. So with this, I'll conclude here, and I'll be very happy to answer questions.
All right, thank you, DK, for going over all of that. We had one question come in.
Yes.
Are you managing the remote hardware using IPMI, BMC, or Redfish?
Not directly. So what we have done, you remember, like we are going through TAPIS. I talked about like the TAPIS has some basic monitoring, basic authentication, scheduling. So we are adding all our components on top of TAPIS. Okay. I don't know whether TAPIS under the hood. I believe it must be using IPMI and all, but I'm not sure about BMC or Redfish. Okay.
Okay. And we also, I've unmuted everybody. So if you have a question, either raise your hand or just unmute and ask your question. Ayush.
Hey, Dr. Panda, it's a great presentation. I just have a quick question. Like, when you say it's at like 2 questions. So the first part is for this, some of the sub frameworks that you presented, does those use like any cloud providers, like cloud computing resources? And the second question is, when you are collaborating with industry partners, what kind of resources does ICICLE provide to the industry partners?
Okay. So two things. So first thing, our broad objective is to really see like this end-to-end to cloud. In the aerial crop scouting, we are actually using cloud, AWS and all. So the drone can directly talk to the AWS. And for the harvest architecture I indicated, currently it is running on like the Ohio Supercomputer Center. We are expanding that into San Diego Supercomputing Center, but we are, as I am talking, actually we are trying to have make it available on the cloud like AWS and Azure kind of things. Okay, so hopefully like in the next 1 year or so, you will see really the solutions being deployed at different places. The second thing with respect to industry, it's a industry partners, like depending on your requirement. We have been talking individually. Everybody, as you know, they have different requirements. So it's actually goes into multiple levels we have with the industry partnerships. Like sometimes they just want an end solution. Sometimes they want to do co-designing. So this will depend on the kind of interest from the industry, and then we take that and then we discuss and see what kind of collaboration will be the best.
All right. Thanks, Dr. Panda.
All right. Well, we're almost at the top of the hour. If anybody has any other questions, please type them or raise your hand. Thanks again, DK, for going through that. If you can send me a copy of the slides, I'll make sure that those get posted.
Yes, I'll do that. So thanks a lot. Thanks a lot for listening. If you have any questions, please send an email to me also later on, and I'll be very happy to talk to you.
All right. Well, thanks, everybody. We're going to be on a couple of week pause here because of the summer holidays. So we will have our next talk on July 12th. So hope everybody has a good weekend and a good couple of weeks, and we'll talk to everybody soon.
Thank you. Bye.